We're starting on our last topic here in Chem 125 in our Advanced Organic Chemistry course. And we've spent our time so far walking around the periodic table, but spending most of our time talking about the chemistry of carbon, because organic chemists love to form bonds to carbon, right? That's carbon-carbon bonds are the basis of organic chemistry. And so we should know a lot about the chemistry of molecules that contain carbon, nitrogen, oxygen. We've covered silicon since pretty much the beginning of the quarter, boron, lithium. And so now, towards the end of the course, we started to talk about elements that don't usually get enough discussion, and that is phosphorus and sulfur. And I think that when we're done with phosphorus and sulfur, we'll have a pretty complete description of organic chemistry and the main elements that you see used in synthesis and chemical biology. So let's go ahead and dig into sulfur. We have to start off by talking about nomenclature. Otherwise, we can't have a common language to discuss functional groups. And so let me start off by doing something a little bit weird, which is talking about inorganic sulfur reagents. Here are some of the most common sulfur reagents that you'll see used. Notice here, these groups are called sulfates. 6 bonds to oxygen, 2 oxo groups, double bond O, 2 oxo groups. That's like sulfuric acid. If you take sulfuric acid and you deprotonate it twice, you would come up with sodium sulfate. I'm not drawing the structure of sulfuric acid. I would assume that you know the structure, the Lewis structure for sulfuric acid. There's another kind of subtle variation of this where you remove one of the oxo groups and you change the oxidation state. So sulfuric acid and sulfate are the most oxidized forms of sulfur, but there's another form of sulfur, and let me go ahead and write out the oxidation state because that's really relatively easy to describe here. This sulfur atom here has 6 bonds to electronegative atoms, so there's nothing weird about having 6 bonds to sulfur. This would be sulfur in the 6 oxidation state. When I come over here to sodium sulfite, that's sulfur in the 4 oxidation state. There's 4 bonds to more electronegative atoms, so that's sulfur in the 4 oxidation state. But the key here is that sodium sulfite has a lone pair, and that lone pair is nucleophilic. So if you walk into any organic chemistry laboratory where people are doing organic synthesis, many or most people will have a bottle of aqueous sodium sulfite sitting on their shelf because you use that to do workups. Whenever you work with oxidants, you want to quench those oxidants. And so people keep a bottle of sodium sulfite or sodium bisulfite on their shelf to dump in and reduce dangerous peroxides or get rid of the excess bromine or reduce the excess MCPBA. That's very common. Okay, let's take a look at an analog of sulfuric acid, an analog of sodium sulfate. And that's if you replace this oxo group here with a double bond S. And in that case, it's the lone pairs here on that sulfur that in this resonance depiction, we've depicted it as double bond S. It's the lone pairs on this sulfur that are the business end of this molecule. Those sulfur lone pairs are nucleophilic. And you use that sulfur atom as a nucleophile for doing SN2 reactions, for reducing peroxides, for reducing excess BR2. So some people have a bottle of thiosulfate on their shelf to use to do workups for reactions that contain excess oxidants when they want to get rid of those. Now, if you look at these structures over here, sodium sulfite and sodium bisulfite, bisulfite means it's just the monoprotonated version, like sodium bicarbonate. Carbonic acid, you deprotonate it once, it's called bicarbonate. Sulfite, right, if it's just got 1 proton and 1 sodium, you call it bisulfite. And still, the business end of this is this lone pair. So sodium bisulfite is used as a nucleophile. The sulfur atom acts as a nucleophile. You can use it to add to carbonyls. You can use it, and it readily dissolves in water. Not much else, but it readily dissolves in water. So of these two, the sodium sulfite is a little bit more nucleophilic. The one on top here, but you have to use that under basic conditions. So if you want something a little closer to neutral, not quite neutral, you typically have a solution of sodium bisulfite because it's not as deprotonated. You can have this under slightly more, not acidic conditions, but slightly more acidic conditions. Okay, so those are the inorganic sulfur reagents. I think if we understand the oxidation states and the importance of those sulfur lone pairs, this gives us a good model to think about organosulfur reagents. Now, it's a little bit trickier here to talk about sulfur 6 and sulfur 4. I'd love to be able to draw some analogy here between sulfur 6 and sulfur 4 here, between the oxidation states. Unfortunately, sulfur is just a teeny, teeny, tiny, eensy bit more electronegative than carbon. It's like 2.58 versus 2.55. So now I'd have to change, right? The oxidation state here depends on having more electronegative substituents like oxygen bound to the sulfur. But now the sulfur is a little bit, the carbon is here is a little bit less electronegative. So we can't use the same oxidation state numbering. So I'm not going to try to assign these as sulfur 6 versus sulfur 4. But let's go ahead and talk about the naming here. The naming is critical. And the naming tells us all about the reactivity of these three classes of organosulfur functional groups. So when I have one carbon atom over here, and then a sulfur with 3 oxygens, we call this a sulfonic acid. Not sulfuric acid, but with that carbon bond, we call it a sulfonic acid. That letter N tells you there's a carbon atom bound to there. And it would have about the same acidity as close to sulfuric acid, right? It'd be about the same. Now, the analog of a sulfite would be something called a sulfinic acid. That N atom there tells me that there's a carbon bound. But the letter I, that one change from O to I, tells me that there's a lone pair on the sulfur. And my eyes are just completely drawn to that lone pair. I want to use that lone pair to do something. We'll see that there's another part of that that's also reactive. Now, when we replace both of those oxo groups and we have 2 lone pairs, this is a weird and wily species that you've never seen before. It's called a sulfenic acid. So you can tell from the letter N here that there's a carbon bound, but that just one change from I to E, sulfinic acid to sulfenic acid. Sulfenic acid tells me there's 2 bonds to sulfur. And this is just a crazy, it's unstable. You've never seen this before. We'll talk about why that's completely unstable, which is why you've never seen it before shortly. But now let's go ahead and drop down below here so we can see as you go in this direction here, you're getting more and more oxidized as you make more bonds to oxygen. And we're going to see the same trend here when we have 2 bonds to carbon. So the names of these functional groups, when you have 2 bonds to carbon, right, this group over here is called a sulfone. You know, there's not a lot of synthetic utility to a sulfone. You usually just put that on there if you're trying to make a drug, right, and you just want to have some polar group there that looks a little bit like a carbonyl with longer bonds. Now, there's another organic chemistry functional group, or organosulfur functional group, that has only 1 oxo group on there. That's called a sulfoxide. And this particular sulfoxide with 2 methyl groups is an extremely common solvent in organic chemistry. It's called dimethyl sulfoxide, DMSO. So we might have seen, I can't remember, reactions in this class that were run in DMSO as a solvent. It has a very high boiling point, so sometimes it's hard to get salts to dissolve in organic solvents. This is about as good as you're going to get if you don't want to use water. Unfortunately, you've got to evaporate the DMSO off somehow. It's hard to evaporate that off because it has such a high boiling point. Okay, the last organochemistry functional group I'm going to refer to as a sulfide. That's with 2 alkyl groups to the sulfur atom. In IUPAC nomenclature, these are not necessarily IUPAC names. IUPAC might call that a thioether. So if I use the word thioether, that's like a regular ether with sulfur instead of oxygen. But we might also call this a sulfide. Okay, so these are our functional groups. And we're going to see there's some very predictable differences in reactivity as we go to fewer and fewer oxo substituents. The more lone pairs we have in the sulfur, we're going to find that it's easier to substitute groups that are attached to the sulfur. And this is the same trend we saw with phosphorus. The fewer oxo double bond O's you have on there, the faster it is to do substitution, the more easy it is to do substitution. Okay, let's go ahead and talk about the basicity of oxygen and sulfur functional groups. I feel like this is one of the most important slides to set you up and thinking about organosulfur chemistry, but it's also going to be one that is hardest for you to remember some real values here. So let me see if I can try to give you some real numbers for basicity. How easy is it to use the lone pairs on these functional groups to pick up protons, right? I mean, Maybe to some extent, picking up, adding to a proton is the same as adding to a carbon electrophile. And so let me go ahead and give you some numbers here that'll tell you about the relative basicities. I could just give you pKa prime values. I'm just going to talk about the relative basicity relative to water, because I think we have an intuition for like how basic is water. You know, the pKa of the protonated water, how acidic would it be if you put a proton on water? Well, the pKa's prime is minus 1.7, but that's kind of too hard to remember. So I'm going to compare everything to water. How easy is it to protonate these other functional groups? If you know how easy it is to protonate water, can you make a guess about how easy it is to protonate one of these other functional groups? I'm going to start off by staying with oxygen. You know, when you go to an sp2 oxygen lone pair, like this one over here on a ketone, or on an ester, or on a carboxylic acid, that's sp2. That's not as easy to protonate. You know, more P character is easier to protonate. It's easier to protonate that. It has more P character in sp3 than over here on a carbonyl. It's harder to protonate carbonyls. How much less harder? I'll give you an equilibrium pKa number. Relative to just water, this is about 10 to the minus 6 harder to protonate. 1,000,000 times harder to stick a proton on a carbonyl. Right? That's how you set yourself up to attack with oxygen nucleophiles like water or alcohols. You have to use sulfuric acid to get oxygen to attack carbonyl groups. In a Fischer esterification, if you're making acetals, and that's not easy. You can't just throw in acetic acid. You throw in sulfuric acid or hydrochloric acid. Now let's take a look at what happens if we compare water, like this, to some sort of organic sulfide. You know, sulfur is not as electronegative as oxygen. Nowhere near. There's not as much partial negative charge on there. It is harder to stick a proton on sulfur, significantly harder. You don't see a lot of reactions that start with protonation of sulfur, and that's because it's so much less basic. So 10 to the minus 5, it's 100,000 times harder to stick a proton on sulfur. Boy, that is not an easy, you know, transition metals love sulfur. Lots of metals love to bind to sulfur, but protons, not so easy. Boy, that's not easy to protonate sulfur. Even I'm just thinking, throwing in hydrochloric acid or other, it's just not easy to stick a proton on sulfur. It doesn't make the sulfur happy. Okay, but let's go ahead and compare what happens if I compare a carbonyl over here, like this one, to S double bond O. Are those the same? Should they behave the same or have the same properties? The answer is no. Because when you look at the relative basicity of a sulfoxide versus a ketone, right? The methyl groups are the same, the oxo group is the same. We're just changing from carbon over here to sulfur. Now, this has about the same basicity as water. It's about as easy to protonate a sulfoxide as it is to protonate water. It's nothing like a carbonyl. It's 1,000,000 times easier to protonate a sulfoxide oxygen as it is to protonate water. And that's probably, if you want to draw a good resonance structure for a sulfoxide, you wouldn't be crazy to draw a resonance structure that looks like this. That's a pretty good resonance structure. When you do that, don't forget there's a lone pair on sulfur. Don't forget that. There's still a lone pair on sulfur. And whichever resonance structure you want to draw with the double bond O or S plus O minus, don't forget there's a lone pair still there on sulfur. But when I look at this resonance structure on the bottom, that's going to explain a lot about the reactivity of sulfoxides. Very easy to protonate that oxo group. So don't forget about that. Well, if one oxo group is great for basicity, and this is the thing that's going to throw you, if putting one oxo group on here makes it super easy to protonate, you'd think two is going to make it better. It's kind of like aspirin. If one aspirin helps, take a bottle full of aspirin. I'm sure it'll help you a lot. I'm just joking there. But it turns out that when you put two of those oxo groups on a sulfur, it is near impossible to do anything with those oxygens. When you look at the relative basicity of this, it's 10 to the minus 15. Man, like, I'm not good with the math here. What is that, 10 to the 9? Like 1,000,000,000 times harder to stick a proton on a sulfone other than relative to a carbonyl group. And it's not easy to protonate a carbonyl. You're never going to see this happen. So forget this. The only thing I've ever in my life seen add to the oxo group of a sulfone is an aluminum reagent. We're not going to talk about that, so forget it. Forget about it. You're not going to see oxo groups on sulfones. Don't try to protonate them. Don't try to use them for nucleophilic attack. Don't draw resonance structures that look like this, because it's not going to help you in any way to draw a resonance structure that looks like this. Right? Sulfone groups are very polar, but that doesn't mean you should use the oxygens to try to do anything, and it certainly doesn't mean you should attack the sulfur atom with anything. So whenever I've seen in class people do things like this with mesylate leaving groups, it's like, oh, I need to protonate that to make it into a good leaving group. No, there's no need to protonate a mesylate to make it a good leaving group. You could never get the proton on there anyways. There's no acid you could ever use that would stick a proton on a mesylate or a triflate or a tosylate. No way you could protonate tosyl chloride oxo groups. Don't try to protonate those oxo groups on a sulfone. Let's just forget about that stuff. So sulfoxide, you can protonate the oxo oxygen. Sulfides, you can kind of get a proton on there, but I can't think of any transformations that require that offhand. So let's start digging in here to go further on the reactivity. So it's this sulfone thing that seems kind of out of whack. It's hard, it's hard for you, based on any simple rationale that we would give you, to anticipate that it would be so hard to put a proton on a sulfone or a sulfonate or a sulfuric acid or reagents like that. Okay, so let's dig into these sulfoxides. Man, those lone pairs on oxygen, they're about as basic as water. They can protonate about as easy as water. And what you'll find is, given the two ends of a sulfoxide that are reactive, there's two sets of lone pairs you want to think about. There's the lone pairs on oxygen, which we just said are about as easy to protonate as water, and then there's these lone pairs on sulfur, and they are both important for organic chemistry. But you can make some rough predictions about which lone pair is going to be reactive when. So there's plenty of negative charge here, partial negative charge on that oxygen atom. And so you will find that the oxygen atom tends to add faster to electrophiles that have a lot of partial positive charge on the electrophilic atom. So what would be some examples of electrophiles that would react faster on oxygen than on the on the sulfur? Sodium would be one. Sodium cation. If you put a sodium cation in there, a lithium cation, it will react faster with the oxo group. Not necessarily irreversibly. That's supposed to be an A. It's not a very well-drawn A. So metal cations, alkali metal cations with a lot of partial positive charge. Acids, strong acids, have a lot of partial, like HCl, sulfuric acid. So I'll just write HCl there. There's a lot of partial positive charge on the proton. The proton is way less electronegative than the chlorine atom or the oxygen atom of your acid. So protons, you'll protonate faster on oxygen than on that sulfur of the sulfoxide. Maybe a little bit, maybe not so surprising, because we've seen this kind of trend before. Silicon, TMS chloride, TMS triflate. Silicon has a lot of partial positive charge on the silicon. If you treat a sulfoxide with TMS chloride or TMS triflate, the oxygen will be the thing that attacks the silicon. And you kind of already know, it's like, oh yeah, well, oxygen loves silicon, silicon loves oxygen. But you kind of already, I hope, you kind of already suspected that would be true. What would be another highly electropositive element that would really go after that oxygen atom? Powerful Lewis acids, aluminum trichloride, boron trifluoride, FeCl3, zinc dichloride. Right? Those types of typical Lewis acids that we've been seeing throughout this course that react with oxygens also react with that oxygen on the sulfoxide, well, preferentially. And the last reagent that is a little bit not obvious here would be powerful acylating agents, like acyl chlorides, anhydrides. This carbon atom right here tends to react faster with things that have partial negative charge. Right, the chlorine, I didn't draw that long chlorine bond, but there's not a lot of resonance on the chlorine lone pairs donating in, but you get the electronegativity effect. So acylating agents, acetyl chloride, benzoyl chloride, will react faster on the oxygen atom of a sulfoxide. So what reacts on the sulfur atom? You want things that are powerful electrophiles but don't have a lot of charge. Let me give you an example of something that would be a powerful electrophile that doesn't have a lot of positive charge. Alkylating agents. Methyl iodide. Right? There is not a lot of partial charge on that carbon atom. That's not why that's reactive. That's reactive because of the long bond. The LUMO is very low in energy because the bond is so weak. You know, long bonds, you got LUMOs that are low in energy and easy to add energy into the LUMO if you draw an MO diagram. So methyl iodide, allyl bromide, things like that would react on the sulfur atom faster than they would react on the oxygen atom. Right? In the Pauling electronegativity scale, carbon is more electronegative than iodine. It's not a lot of partial positive charge on the carbon there. So methyl iodide alkylating agents are reactive not because of charge. They're reactive because of those long bonds, typically. Okay, so it kind of seems like you ought to draw this other resonance structure where it's O minus and S plus. Maybe that explains a lot about what's going on here. But let me just warn you: don't treat a sulfoxide oxo group like a carbonyl group, because and the reason is I've already told you over and over again up above here that this lone pair can definitely add to electrophiles like this, right? That's or to acetyl chloride or chlorosilanes or things like that. But I want you to remember: do not ever take a sulfoxide and do this. Don't try to attack that. It is not a carbonyl. You will not be able to attack a neutral sulfoxide with a nucleophile, with nucleophiles that we talked about in this class. So don't carry this resonance structure too far. It's great for understanding the reactivity of the oxygen atom, but don't think that you can easily add nucleophiles to just a regular sulfoxide. Unless you do something, you'd have to do something to this. You'd have to do something to this if you wanted to add a nucleophile into the sulfur atom. You can't just take nucleophiles and add them into DMSO. Okay, so man, I just feel like I want to use this to make bonds to carbon using acetyl chloride or silylate it or protonate it. We'll see some reactions of this sulfur lone pair, but not too many. Up until now, we've been comparing sulfur and oxygen lone pairs and the relative nucleophilicity of those in a sulfoxide. But I want to talk about the relative reactivities of two types of sulfur lone pairs: a sulfur lone pair on a thioether versus a sulfur lone pair on a sulfoxide, because one of those is much more reactive than the other. And I'm going to give you an example of a special type of SN2 reaction that leads to oxidation of the sulfur. So we're going to talk about oxidation of this sulfide using a common oxidant, MCPBA. You could also use hydrogen peroxide, which has a weak oxygen-oxygen bond, or bromine with a weak Br-Br bond, or iodine with a weak iodine-iodine bond. It's all the same example. And we're going to draw out the mechanism for oxidation with MCPBA by drawing out a classical tautomer here that we've been using for arrow pushing. So let me go ahead and draw that out. What does that oxidation look like if we draw out this common tautomer that we draw when we draw oxidation with a peroxy acid? So you may recall when we did oxidation of alkenes with peroxy acids, we drew out MCPBA in this particular tautomer. We transfer the proton to the carbonyl, and that allows us to see that the leaving group is going to be a carboxylic acid. And in fact, the mechanism here is simpler than for epoxidation. We're simply going to take this lone pair on the sulfur, one of the two lone pairs on the sulfide sulfur, and then just simply do an SN2. And I'm going to push the arrows all the way around here so that you can see that I would generate a carboxylic acid byproduct. So that's the mechanism for oxidation of a sulfide to give a sulfoxide. And there's a common resonance structure that we draw for sulfoxides. I feel like half of the time I draw the sulfur with double bond O resonance structure. The other half of the time I draw this resonance structure that has S plus O minus. Either one is fine, and maybe it just depends on how much I care about the relative reactivity. So it's easier to draw this resonance structure that has S double bond O because there's fewer charges to draw there. I oftentimes like to draw the lone pair on this sulfoxide sulfur just to remind myself that they're there. But really it's the bottom resonance structure that I think is usually informative to you, because oftentimes we're using the oxygen as the nucleophile. But in this case, we're talking about the reaction with peroxy electrophiles. And we don't want to form an oxygen-oxygen bond, so we're not going to use the O- as the electrophile. If we treat this with a second equivalent of MCPBA, or hydrogen peroxide, or chlorine, Cl2, with a weak chlorine-chlorine bond, it's the lone pairs here on this sulfur atom that are going to react. And so we would end up, doesn't matter which resonance structure we use, we're going to end up with a sulfone if we treat this with a second equivalent of an oxidizing agent like MCPBA. And what that means is every molecule of MCPBA, every molecule of peroxy acid in there, like MCPBA or hydrogen peroxide, reacts more quickly with the sulfoxide lone pair than with the sulfide lone pair than it reacts with the sulfoxide lone pair. So halfway through the reaction, we have an equal mixture, a 50-50 mixture of sulfide and sulfoxide, but the sulfide lone pair is always more nucleophilic than the sulfoxide lone pair. No problem getting that to stop right here. And if you want, then you can add a second equivalent of your oxidizing agent to go all the way to the sulfone oxidation state. Okay, sulfur lone pairs, thioether lone pairs are reactive. It's easy to oxidize sulfur lone pairs by getting them to act as nucleophiles. I'm showing you an example below just to remind you that lone pairs are more nucleophilic in general than pi bonds. That shouldn't be news to you. We've been talking about that general ordering. It's definitely true in the case of a third row atom like sulfur that has very reactive lone pairs. So if we treat this thioether here with MCPBA or hydrogen peroxide or some other oxidizing agent, even though we've got all these other pi bonds in here, the only product that you get of this reaction in high yield, you get this product, is oxidation of the sulfur atom, right? That's the preferred site of oxidation. Even though there's an alkyne that has 2 pi bonds in there, even though there's not just an alkene, but a diene. Dienes are way more nucleophilic than regular alkenes, and yet you specifically oxidize, in this case, not just once, but because they add a second equivalent, you oxidize twice. So the lone pairs on both the thioether starting material and the sulfoxide intermediate, those lone pairs on sulfur are more reactive than the double bonds in this reaction. Okay, so oftentimes you want to use sulfur lone pairs as nucleophiles, but sometimes you want to attack carbon, not oxygen or halogen to do an oxidation. And let's take a look at that. So here's an example where we're using the lone pairs on a thioether, there's 2 lone pairs on there, to do an SN2 reaction on carbon. That should seem pretty natural to you. Here I'm taking an example of an exceptionally good substrate for SN2, an allyl bromide. Right? It's very hard to do competing eliminations on allyl bromide, so you get very fast rates of SN2 and no E2 elimination byproducts. But you notice when I draw the products out over here, the product doesn't have a simple allyl group on there. You get this whole mixture of products. Some of them have allyl groups. Like look at this product you get over here. It's got 2 allyl groups. Where did that come from? What happened to the benzyl group that was on there in the beginning? Or how come this one ended up with 2 benzyl groups? So to help us understand what's going on here, when we do this reaction, let's go ahead and draw out the mechanism for this process. So the first step is a simple SN2 process that looks like this, where we're going to do an SN2 reaction, and our initial product out of that process is going to be a sulfonium ion. So 3 bonds to oxygen, we call that an oxonium ion. 3 bonds to sulfur, we're going to call that a sulfonium ion. And the counter ion to that sulfonium ion in here is bromide, which is a decent nucleophile. What this example shows you or reminds you is that not only are sulfonium ions the products of these SN2 reactions, but they're also good substrates for SN2. So if I have that bromide ion sitting around in here, right, it's not easy to isolate this very quickly, because as soon as you form this sulfonium ion, that bromide ion is getting ready to do SN2 again. Now, it could do SN2, sorry, I didn't finish my allyl group here. It could do an SN2 reaction in order to regenerate the product. That's definitely happening. That SN2 process would be reversible, but I'm not going to draw that because I don't want to confuse us. I'll just draw a backwards arrow here to remind you that that initial SN2 to make the sulfonium is reversible. You can go right back to the sulfide and to allyl bromide. But sometimes that that bromide group is going to attack somewhere else. Like it could attack over here on that benzyl group and then generate benzyl bromide and a different thioether. Or it could attack over here on the methyl group, right there, and give you methyl bromide. In fact, all of those things are occurring in this reaction mixture. So you're getting SN2 attack at all the positions that are easy to attack. So for example, if I attack that benzyl group, I'll end up with benzyl bromide here as my byproduct, and I'll end up with this thioether that in that reaction that would look like this. And so I would end up with both of those. But you know what? Those are both reactive. So this benzyl bromide can now start to react with more of the starting material or with any other group that's in there. So let's take a look at what would happen. If that benzyl bromide now started to react with the starting material, right here's a molecule of the starting material, that can undergo SN2. And you may not want this to happen, but this would all be happening unstoppably in this reaction mixture. And this other thioether that we generated right here, that thioether could also undergo reactions with some of the allyl bromide that was in there, right? That was one of your starting materials. And so let's see what happens here if we have another molecule of that allyl bromide in there in this sulfur lone pair, right? That sulfur lone pair can come back around and attack and make a sulfonium ion. So you get this whole mixture of sulfonium ions because these SN2 exchange reactions are so rapid. It's easy to do SN2 on sulfonium ions to break carbon-sulfur plus bonds. You can also see alkylation of sulfoxide lone pairs. So here's an example down below. But just as with the oxidation reactions with MCPBA on the bottom here, that sulfur lone pair on the sulfoxide is not as reactive as a thioether lone pair. So you'll notice here that in this reaction, to get that sulfoxide lone pair to react, they had to heat this reaction. They had to heat it at 80 degrees for a day in order to get this SN2 to react, this SN2 reaction to proceed. It doesn't occur as fast as when you're using a thioether lone pair to attack, but you can get that to react. And this type of salt product that you generate here is not a sulfonium ion. We call that a sulfoxonium ion. And you'll see that a little later towards the end of this topic. Okay, so you can use sulfur lone pairs to attack carbon in order to generate sulfonium ions and sulfoxonium ions. Let's go ahead and continue on with reactions of sulfoxides. If you tell anybody that you took a class in advanced organic chemistry and tell them that you covered sulfur chemistry as one of your topics, they are probably going to expect that you were introduced to this reaction, this classical reaction called a Pummerer reaction. So let's go ahead and take a look at this Pummerer reaction that is so well known and kind of an expected topic for coverage when you talk about sulfur chemistry. And this is a particular reaction of sulfoxides. And you know, it looks deceptively easy when you first look at it because you might be thinking, oh, I can see what's happening here. We're just taking an acetylating agent and we're making an acetyl group add to oxygen. Here's the oxygen, here's the acetyl. You've seen making esters out of alcohols, but notice that the ester group is now attached on the carbon atom, not on the sulfur atom. Something has happened there. If you look a little more deeply, you can see that this CH2 group in the starting material is now oxidized in the product. It's now a CH with an extra carbon-oxygen bond. So let's go ahead and talk about what's happening here. So when you take electrophiles that have a lot of positive charge on them, like silyl chlorides, for example, protons or acids like sulfuric acid, it's the oxygen atom of the sulfoxide that reacts the fastest. And so the mechanism starts off with us using that O- lone pair, and we acylate that. More specifically, we acetylate that oxygen. I'm not going to draw both of those steps of that acetylation process. You should have seen this enough times, acetylation with acetyl chloride, acetylation with acetic anhydride, that you would know the mechanism for that. Let's go ahead and just draw out this intermediate. And I'm going to draw this alkyl chain sticking off that CH2 as an R group. And then over here, we've got that acylated, that acetylated, I'll just write AC here for an acetyl group, that acetylated sulfoxide. And we still have that positive charge on that sulfur atom. So it's a kind of sulfoxonium ion. It's a sulfonium ion of some kind. This one has an oxygen substituent, not just carbon atoms. Now what you wouldn't realize is that sulfonium ion, all sulfonium ions, are easy to deprotonate. If you put 3 methyl groups onto a sulfur and have a sulfonium ion with 3 methyl groups, the pKa of these CH2 groups over here, the pKa of these CHs that are next to an S plus for 3, if you just have 3 methyl groups, that's got a pK of around 18. And with that oxygen here, that's even easier to deprotonate. I don't know what the pKa is, but it's lower than 18. You know, water has a pK of 16. I would guess this pKa of that CH there is about the same as water, or maybe lower. It's very easy to come along and deprotonate this, so it's totally plausible under the conditions of the reaction, since you're doing this in pyridine, that the pyridine could act as a base to deprotonate this. It's so acidic next to that S+. Now I'm going to put the electrons right here and just leave them on carbon. Now in theory you could draw a resonance structure where you draw an S double bond C, but you know you don't get stable pi bonds to 3rd row, 4th row, 5th row atoms. So we're better off drawing this out as this Illid intermediate that looks like this, with carbon minus, kind of like we do for a Wittig reagent. Let me circle that minus so it's clear that it's a charge. Plus charge on sulfur, and we've got this acetate group here. And now next what happens is something like an E1, we're doing an E1CB elimination mechanism. When you do an elimination via the E1CB, you make a stable carbanion and use that carbanion to push out the leaving group. And the acetate is our leaving group here, in this case, in a Pummerer reaction. Let me go ahead and draw that out where we're just pushing that out. And so we generate a new type of sulfonium ion. Sulfur with 3 bonds is a sulfonium ion. So let me go ahead and draw out that sulfonium ion intermediate like this. You know, there was a sulfur lone pair on here the whole way through, and just so we don't, it'll drive me crazy if I don't draw that lone pair, even though we're not going to use it. That'll allow you to see why that's bent. So we get this new kind of sulfonium ion. That means 3 bonds to sulfur, and 1 double bond and 1 single bond. That's a new type of sulfonium ion, and that's electrophilic. But the acetate byproduct that you generate out of this doesn't attack the sulfur again. It attacks the carbon atom. So it should kind of look like a carbonyl to you at this stage, like a protonated carbonyl. It should make sense that you want to break that weak sulfur-carbon double bond. Carbon-oxygen double bonds, you can attack those, and those are way more stable, but a sulfur-carbon pi bond, that doesn't have a lot of pi character in there. Easy to add to that using acetate or some other nucleophile. And that's what leads to this, this thioacetal byproduct. Usually people don't want those thioacetal byproducts. They take those and they isolate those either in a workup with either acid or hydroxide nucleophile, and it ends up converting that into an aldehyde. So oftentimes this process is called a Pummerer oxidation, where you take a sulfur carbon bond you don't want, like this one over here, and then you convert that into a carbonyl group that you do want. So you can do aldol reactions or other synthetically useful processes there. Now this E1CB elimination mechanism, that's the most plausible mechanism, but you will often see this elimination process depicted as a concerted E2 process, where it's all done in one step. And there's no evidence for that, but I would accept that mechanism if you drew out this as a concerted E2 elimination, just because on so many websites you'll see it drawn out as this concerted E2, but there's no evidence that that goes through a concerted E2 process under the conditions that I've drawn here. So I like the sulfoxonium illid, the E1CB mechanism. You wouldn't draw an E2 mechanism for in an aldol reaction. And so similarly, this is set up for an E1CB, but I'll accept the E2 elimination, one-step elimination mechanism if you draw it that way, if you choose to draw it like that. All right, let's go ahead and talk about substitution at sulfur. So sulfur, we've been talking about the nucleophilicity of the sulfur lone pairs, but what about when you attack and you displace leaving groups that are attached to sulfur? So here I've drawn some examples where I've got a great leaving group attached to sulfur. Chlorine atoms, are great leaving groups. So you can imagine substituting the chlorine atom on those groups. So over here I've got a sulfonyl chloride, not a common reagent. You've never seen anything like that before, a sulfonyl chloride reagent. It's kind of astounding that you can isolate that kind of stuff and work with it. Sulfonyl chlorides, those are commercially available. They're not very common, but they're commercially available and stable. And you should have, from the very beginning of any introductory organic chemistry class, learned about sulfonyl chlorides, like tosyl chloride. And you should know that you can substitute that chlorine atom with an alcohol to make a tosylate leaving group. That should be well understood by you if you're taking a class in advanced organic chemistry. Now let's go ahead and think about the substitution processes here, because they do not all occur at equal rates, and the substitution of the chlorine doesn't all occur through the same mechanism. So I've tried to divide this up kind of conceptually into two groups here, depending on the mechanism. Is the mechanism a concerted displacement of the chlorine, or does the mechanism involve addition, elimination? So with sulfonyl chlorides, those displace through SN2 reactions. Man, I am oftentimes in this class disparaging SN2 processes at carbon and telling you, oh yeah, that's not a very good reaction. Sigma star on carbon is not very easy to add to. But man, you take this sulfur chlorine bond, that long bond to third row atoms, that bond is easy to displace. This is a lightning fast SN2 reaction. And if I want to think in my mind, I want to think about a good concerted displacement process, sulfonyl chlorides are so easy to do SN2 at those bonds. So doing SN2 at carbon, not so easy. Doing SN2 at divalent sulfur, super easy. Okay, but when we come over here and we put this double bond O on here, this oxo group, as in a sulfonyl chloride, or in a sulfonyl chloride like these here, now when you attack, it's not a concerted displacement of the chloride anymore. You do attack from the back side of this chlorine bond, but instead of kicking out the chlorine, you push the electrons over to one of those oxo double bond oxygen atoms. So you go through an intermediate. It's not a concerted displacement of that chlorine leaving group. So I'm going to draw this out as O minus there. There's still a lone pair here. This goes through a trigonal bipyramidal intermediate, not a transition state, but an intermediate, in which that nucleophile is now attached. And now the lone pairs on here can push out that chlorine leaving group in a second step. So this is a two-step elimination process, not a one-step elimination process for substitution at sulfonyl chlorides. And there's a lone pair here, and now my nucleophile would be attached. And it's the same two-step mechanism for tosyl chloride or any sulfonyl chloride, except for mesyl chloride. We've talked about that special mechanism before. But most sulfonyl chlorides, under most conditions, substitute through this special, through this two-step addition-elimination mechanism.